Hello. This series of short talks follows on from the earlier talks about electric and magnetic fields and looks at what happens when you consider the interaction between magnetic fields and electric fields and currents. And this is the subject known as electromagnetism. What we'll be covering that's new is looking at a classic experiment done by the Danish physicist Ørsted, in which he showed that a current creates a magnetic field. It's almost the inverse to Faraday's classic experiment, where he showed that a changing magnetic field can produce a current. We'll also be looking in a bit more detail at some magnetic materials, in particular ferromagnets, and showing their role in inductors. In this first short talk, however, I just wanted to do a quick revision of electric magnetic fields and the concepts of flux. I hope you'll remember that there are two ways to graphically represent an electric field. One is in terms of a length of an arrow representing the magnitude of the field, and the other is in terms of these things called flux lines, where it's the density of the lines which represent the strength of the field. And if you remember, the field strength is the force that would be exerted on a unit charge. The electric field strength is given by this formula here. This would be the electric field due to a charge Q1, a distance r away from that charge. 4 pi and epsilon naught are constants. Note that this would only apply in free space. There's an equivalent formula for magnetic fields in terms of these magnetic charges, which don't really exist in the same sense that electric charges exist, but they provide a very convenient mathematical technique for analysing magnetic fields. You can use all of the same equations and theories as you can for electric fields just by assuming these magnetic charges. There'd be a positive magnetic charge at a north pole and a negative magnetic charge at a south pole. Since magnetic charges always appear in pairs, we get field lines characteristic of a dipole. That's a positive charge and a negative charge close together. If you remember the demo, these are electric field lines where the length of the arrow represents the magnitude of the electric field. If you represented the same situation in terms of flux, you'd get a picture like this. This is a positive charge, so the flux is streaming away from the positive charge. If I move the positive charge a little distance and then add a negative charge, then we get the characteristic flux pattern of a dipole. Also, a quick reminder of the phenomena of polarisation, which is why people put dielectric materials between the plates of a parallel plate capacitor. The idea being, if you have a dielectric material, that's an insulator which doesn't conduct electricity, you will still have negatively charged electrons orbiting around positively charged nuclei, the so-called classical model of an atom. We know it's not particularly accurate these days, but it will do as a good explanation of why polarisation works in capacitors. If you put on an external electric field, then the negatively charged electrons will be attracted to the source of the electric field, and the positively charged nuclei will be repelled from the source of the electric field, so the electrons will start on average to move a little bit towards the source of the electric field. So the electrons will on average move a little bit towards the source of the field, and that results in each atom becoming a dipole. where the negatively charged electrons are slightly offset from the positively charged nucleus on average. All of these dipoles add up and create an electric field which tends to oppose the direction of the external field. And that is known as the polarisation field, the result of all of these dipoles. The electric field inside the dielectric is therefore smaller than the external electric field, although it does go in the same direction. And if you're reducing the electric field inside a dielectric, then you are reducing the total potential difference between one side and the other. And since Q equals CV, if we reduce the potential difference for the same amount of charge being stored on the plates of the capacitor, then we must have increased the capacitance. And increasing the capacitance for a given size of component is a good thing. Quick quiz question just for fun before we leave this introduction talk. True or false? Does the Earth have a large bar magnet inside it, or at least act as if it has a large bar magnet inside it with a north pole towards the North Pole? Answer? False. It doesn't. It's the other way round. Because magnets are a bit like electric charges in the same sense that like poles repel, but unlike poles attract. But the compass needle is a magnet which can rotate with a north pole towards the north end and a south pole towards the south end. So if the north pole is going to be pointing north, then there has to be a south pole inside the Earth towards the north pole of the Earth. So that the north pole of a magnet, i.e. a compass, will point north. So, rather bizarrely, there's a big south pole near the North Pole, and there's a big magnetic North Pole near the geographic South Pole. That's all I wanted to say for this introduction talk. Next time we'll get on to some new material, including the classic experiment by Hans Christian Ørsted.